All right, in 3.5, we are going to do the exact same things as we did in the last section. We are just going to now include complex roots, right, or imaginary roots. So, real quick, just a review of some theorems and definitions. The factorization theorem just says that a polynomial has a factor if and only if that value that we are subtracting in the factor is a zero. Right? That's what it means to be a factor. Right? Or in other words, every root of a polynomial can be written as a factor in the form of x minus that root. The number of zeros theorem that we looked at before said a polynomial of degree n can have at most n real zeros. So a fifth degree polynomial could have at most 5 real zeros. But now, if we include complex roots, right, or imaginary roots, and account for the multiplicity of zeros, a polynomial of degree n has exactly n roots. So a 13th degree polynomial will always have 13 roots. Okay, again, that's including imaginary roots and accounting for multiplicities. All right. The conjugate pairs theorem says the one that we looked at said if an irrational number is a root, then its conjugate is also a root. So in this section, we're also going to look at complex numbers. Okay, so a complex number is an imaginary. So something like 4 minus 5i. If 4 minus 5i is a root, then 4 plus 5i is also a root. Right? Irrational or complex numbers always have to come in conjugate pairs when we're talking about zeros. And then the definition of I, right? I is an imaginary number, and it's defined as the square root of -1, right? So another key here that we're going to be including in this section is I squared. I squared would be the square root of -1 squared. That we say is just equal to -1. And that's going to be key in solving some of these problems here. Right? So our first example, right, is finding a polynomial having the specified degree, leading coefficient, and zeros. Okay, so in this example, we want to write a polynomial that has a degree of 3. That means I'm going to have 3 factors, right? So a degree of 3, let's make a note, means 3 factors. I'm going to have x minus something 3 times. The leading coefficient is going to be 2, right? So that's just going to be the number out in front. And then they give me 2 zeros, 5 and -3i. Well, up top, we just said in our conjugate pairs theorem that if we have an imaginary root, right, or a complex root, then its conjugate also has to be a root. So if -3i is a root, then +3i also has to be a root. Okay? So the way that we're going to write this out, I'm going to say that my function is, now I know that my leading coefficient is 2, so I'm just going to go ahead and throw that out front, and then I'm going to write each of these as a factor. So it's always x minus the 0, so x minus 5, then times x minus -3, so x minus -3 would actually, I'm sorry, x minus -3i would actually be x plus 3i. And then my final root will be x minus 3i. Now, the directions do specify that we want to write this polynomial in standard form with real coefficients. What that means is we just want to multiply this out. When I multiply all of this out, I should not have any i's in my final answer. Every coefficient should be a real number. To do this, we are going to start by multiplying the 2 complex roots together. Okay, so I'm just going to leave this 2 times x minus 5 out here. And then I'm going to multiply these 2 together. So I'm going to multiply first. So x times x is x squared. Then x times -3i would be -3ix. Then 3i times x would be plus 3ix. And then positive 3i times -3i would be -9i squared. Okay, so we can clean this up a little bit here. So we'll have 2 times x minus 5 times x squared. Then negative 3i and positive 3i, those just cancel out, right? And I'm left with minus 9i squared. Now, we just said that I squared is actually equal to negative 1. Okay, so let me put this in a different color here. So this part here would actually be negative 9 times negative 1, right? I squared is just equal to negative 1. So when I'm simplifying this, negative 9 times negative 1 would just be plus 9, right? This whole thing would just simplify to x squared plus 9. So now we can keep multiplying this out, right? It actually does not matter if I distribute the 2 in here first or if I multiply this times this first. Okay, I'll multiply the binomials together first. So x times x squared would be x cubed, x times 9 would be 9x, negative 5 times x squared, negative 5x squared, and negative 5 times 9 would be minus 45. So finally, we just want to multiply everything by 2. And as I'm doing that, I'm going to put these in the correct order of descending power. So 2 times x cubed. Then my next power is squared. So I'm going to do 2 times negative 5x squared. That would be negative 10x squared. Then 2 times 9x. And 2 times negative 45. So this would be my final answer. Okay? This polynomial satisfies all of these parts of the problem. It is third degree, the leading coefficient is 2, and the three zeros are 5, negative 3i, and positive 3i. Okay, so we start with this and multiply it all out. Let's take another example like that. Okay, we have another third degree here. This time we want a leading coefficient of negative 4, and then again they give us two zeros, 2 and 1 plus I. Well, again, the conjugate here would also have to be a 0, so 1 minus I would have to be a 0. So let's start the same way we did before by writing out the factors. So my leading coefficient is negative 4. One of my factors will be x minus 2. Now, we need to be careful with how we write these factors. Okay, it's always x minus the factor. So in this case, the factor is 1 plus I. I need to be really careful here that I put that whole thing in an extra set of parentheses in there. I'm doing x minus that whole factor. Same thing for the second one. It's going to be x minus that whole factor, x minus 1 minus I. So now before I start multiplying these out, we can clean up that a little bit inside. So I'm going to distribute this negative sign through the parentheses, and this will just become x minus 1 and then minus I. Then here, if I distribute the negative through, I would have x minus 1, and then this would become plus I. Okay, so when we're setting this up initially, we have to be careful that we are putting that entire factor in parentheses and subtracting. So now I want to multiply my two imaginary roots together. Now this is a trinomial times a trinomial, so I'm going to have a few more factors to keep track of. All right, so I'll multiply this first term by all three of these first. So x times x is x squared, x times negative 1 would be negative x times I would be ix. Then take the negative 1 and multiply by everything. Right? So I will have negative 1 times x would be minus x. Negative 1 times negative 1 would be plus 1. And negative 1 times I would be negative I. Then finally, take the negative I and multiply by everything. So negative I times x would be minus ix. Negative I times negative 1 would be plus I. And negative I times positive I would be minus I squared. All right, so we need to clean this up a little bit here. Right? So I'll list this out first. Negative 4 times x minus 2. Then the inside of my parentheses, the x squared has no like terms, so that's going to stay. Then I've got negative x minus x. So that would be minus 2x. Okay, so we've taken care of those. Then I've got plus ix minus ix. Those are going to cancel out. Then I've got, let's see, minus I plus I. Those cancel out. And then I actually just have 1 minus I squared. And remember, I squared is equal to negative 1. So this would be minus negative 1. So we actually have 1 minus negative 1. 1 minus negative 1 would be 1 plus 1. So this would be plus 2. All right. So now I can multiply this binomial times this trinomial. So x times x squared would be x cubed. X times negative 2x would be negative 2x squared. X times 2 would be 2x. Then negative 2 times x squared minus 2x squared. Negative 2 times negative 2x would be plus 4x, and negative 2 times 2 would be minus 4. So I can combine a couple of things in there. So negative 2x minus 2x would be minus 4x squared, right? And then plus 2x plus 4x would be plus 6x. And then finally, multiplying the negative 4 through, we'll have negative 4x cubed plus 16x squared minus 24x plus 16. Okay, so this polynomial would satisfy all of my constraints up here. Third degree, leading coefficient of negative 4, and 3 zeros would be 2, 1 plus I, and 1 minus I. All right? So next, let's just take a look at solving a few polynomials that have imaginary roots. Okay? This first one is already completely factored for us, so all I need to do is set each of these individual roots equal to 0. So x plus 1 equals 0, x minus 2i equals 0, and x plus 2i equals 0. And all I need to do then is subtract 1, I'll get x equals negative 1, add 2i, so x equals 2i, and subtract 2i. We'll get x equals negative 2i. Okay, so 3 factors, 3 roots. Right? The next one is not factored for us. Okay, and this is a sum of squares, so we actually cannot factor it. But what I can do is subtract the 81 over. I'll get x squared equals negative 81. And then I can take the square root of both sides. Now, when I do this, okay, again, we need to include the plus or minus, but this negative, I'm actually just going to rewrite this as the square root of negative 1 times the square root of 81. Right? Whenever we have a negative inside of a radical, I can rewrite it like this. So then I know that the square root of negative 1 is just I. And then the square root of 81, that is a perfect square, so that would just be 9. And then the general convention is to write this as 9 times I. And if we have a number, we write that out in front of the I. So the two roots of x squared plus 81 would be positive 9i and negative 9i. All right, let's try another one. So here, x squared plus 5x equals negative 7. Right, well, there's a couple of ways we could solve this. We could complete the square, right? Or we could use the quadratic formula. Personally, I'm probably a little more comfortable using the quadratic formula, but that is totally up to you. I'm going to do this using the quadratic formula. So what we would need to do is add the 7 over, get everything on one side equal to 0, and then I'm just plugging these into the opposite of b plus or minus the square root of b squared minus 4 times a times c. Okay, so remember the coefficient here is a, coefficient here is b, constant is c. That's all over 2 times a. And then we just simplify. So this would be negative 5 plus or minus the square root of, so 25 minus 28, right? 4 times 1 times 7 would be 28. So 25 minus 28 would get me negative 3. And then I can simplify, just like we did on the last problem. This, the square root of negative 3, I can rewrite that as the square root of negative 1 times the square root of 3. And then the square root of negative 1 is just I. So I can write my answers here as negative 5 plus or minus I times the square root of 3 over 2. Now, it is convention if we have a square root to write the I first. Okay? If we end up with a whole number, we would write the I second. All right. One more example here. Okay, this one we have a cubic. Now, we could, like we have been doing, list out our possible rational zeros, synthetically divide until we find a 0, and then solve the remaining quadratic. But there is another possibility. This one is actually set up to do factor by grouping. Okay, I can group the first two, group the second two. Now, if you recognize that on a problem like this, it's going to save you a lot of work. And what we're looking for is that I can take a factor out of the first two terms. So the GCF, the greatest common factor of 2x cubed and x squared would be x squared. And if I take out an x squared, what I'm really doing is dividing each of these terms by x squared. I would be left with 2x plus 1. Then if I look at my second two terms, the GCF there would be 9. I could take a 9 out of both of those, and I would be left with 2x plus 1. Right? That's what we're looking for when we're doing factor by grouping. If I can take something out of these two terms and these two, and I'm left with the exact same thing, then I can factor by grouping. So essentially what we're doing then is factoring a 2x plus 1 out of each of these. So if I factor 2x plus 1 out, then I'm just left with x squared plus 9. And then I can set each of these factors equal to 0 and solve. So 2x plus 1 set equal to 0. I'll subtract the 1 over, divide by 2, and I'll get that one of my roots is negative 1/2. Then I've got x squared plus 9. I'll subtract the 9 over, take the square root, and we'll get x equals plus or minus the square root of negative 9, which we can simplify, right, into the square root of negative 1 times the square root of 9, which would get me I and 3. So this would just be plus or minus 3i. So we get three roots, negative 1/2, negative 3i, and positive 3i. All right. The last thing that I want to do is go through a couple of problems that are going to be just like what we did in the last section, where we need to list out our possible rational zeros, try to find a possible rational zero by synthetically dividing, and then once we get to a quadratic, we can just solve that using the quadratic formula. So here, right, first, we would actually want to list or to find how many positive roots, how many negative roots we would have using Descartes' rule of signs, just like in the last section. So here, if we're looking at positive, negative, positive, positive, we end up seeing two variations in sign here to here. So we could have 2 or 0 positive roots. Okay, and remember, if we see two variations in sign, that's the number we start with, and then we just start subtracting 2 to see how many possibles there are, right? So for example, if we had some huge polynomial and we saw 13 sign changes, well, we could have 13 or 11 or 9 or 7 or 5 or 3 or 1 positive roots, okay? Then we want to plug in negative x, so negative x cubed minus 5 times negative x squared plus 7 times negative x plus 13. So that's going to be negative x cubed. Then this would stay positive, right? So that would actually be minus 5x squared minus 7x plus 13. So we've got negative, 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 positive. So we only have one sign change here, one variation in sign. So that means we're going to have one negative root. So now we want to start by looking at the possible rational zeros. And remember, that's just all of the factors of the constant over all of the factors of the leading coefficient. And here we only have a couple of possibilities. Okay? 13 is a prime number, so its only factors are 1 and 13. And 1's only factors are 1. So we only end up with 4 possible rational zeros. And now remember, this polynomial may not have any rational zeros. That is a possibility. Okay? But if it does, it has to be one of these 4 values. So let's start by synthetically dividing. Start with 1. So if I list out my coefficients, bring the 1 down, and multiply, add, multiply, add, multiply, add, and 1 is not a root. Okay, so let's try 13. So 1, negative 5, 7, 13. Bring the 1 down, multiply, add, multiply. So 13 times 8 is 104. I mean, we can already kind of see that this isn't going to work. Add, multiply, and add. 4, 5, 6. So let's try a couple of the negative values. Let's try negative 1. And so bring the 1 down, multiply, add, multiply, add, multiply, and add. And we see that negative 1 is a root. So we have a depressed polynomial now. Since I started with a third degree, that means that this will be a second degree. X squared minus 6x plus 13. And to solve this, we can use the quadratic formula, right? So x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. So that'll be 6 plus or minus the square root of, so that'll be 36 minus 4 times 13. So 4 times 13 would be 52. So 36 minus 52 would get me negative 16 all over 2. So the square root of negative 16 would be the square root of negative 1 times the square root of 16, which would be I times 4, or just 4I, all over 2. And then since these are both divisible by 2, 6 divided by 2 would be 3, and 4 divided by 2 would be 2. So I end up with 3 plus or minus 2I. So my three answers would be -1, and then 3 plus or minus 2I. All right. Now, I do want to point out that in our Descartes' rule of science, we ended up with 0 positive roots and 1 negative root. Okay? Imaginary numbers are neither positive nor negative. Okay? So we had 1 negative root and 0 positive roots. All right? One more example. Okay? So here, again, we would want to start by finding the positive and negative possibilities. So plus, minus, plus, minus, plus. So I'm changing sign 1, 2, 3, 4 times. That means I could have 4 or 2 or 0 positive roots. Then plug in negative x. So that'll be negative x to the fourth minus 8 times negative x cubed plus 22 times negative x squared minus 28 times negative x plus 16. So that'll be positive x to the fourth plus 8x cubed plus 22x squared plus 28x plus 16. Did I do that right? Yep, double negative, that'll be positive, double negative. So we have plus, 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 0 variations in sign. That means I know I will have 0 negative roots. For my possible rational zeros then, that actually means I can exclude all negative values. I don't have to write the plus or minus for this problem. So my possible roots are just all the factors of 16 over 1. So that would be 1 and 16, 2 and 8, and 4 and 4. So these are the only possibilities for the possible rational roots. So let's start by plugging in 1. So listing out my coefficients, and let's synthetically divide. So bring the 1 down, multiply, add, multiply, add, multiply, and add, and we see that 1 is not a root. Let's try 2. Plug 2 in. So bring the 1 down, multiply, add, multiply, add, multiply, add, multiply, and we see 2 is a root. So since I started with a 4th degree, that means this will be a 3rd degree. So this will just be x cubed minus 6x squared plus 10x minus 8. So let's try our next possible rational zero. So let's divide 4 in. My coefficients are 1, -6, 10, and -8. So bring the 1 down. Oops, it should be a 1. Bring the 1 down. Multiply, add, multiply, add, multiply, and add. And we get that 4 is also a root. So let me highlight those. We found 2 roots already. And now we just have a quadratic left to solve. So this would be 1x squared minus 2x plus 2. And we can use the quadratic formula to solve this. So x will be the opposite of b, plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that'll be 2 plus or minus, this would be 4 minus 8. So that would be negative 4 over 2. So this would be 2 plus or minus the square root of negative 4 would just be 2i over 2. And then both of those are divisible by 2. So we would get 1 plus or minus I. So my four answers, okay, we had 2, 4, and 1 plus or minus I. All right, that is it for this video. Final question is going to pop up asking you what questions you have.